Hello, my name is Yuzhuang Chen, and this is a project for the EL6825 pattern recognition class. And in this project, we're going to focus on the low light image enhancement. So first of all, please allow me to briefly introduce the reason why I choose this topic. With the fast-growing market and continued development in hardware and software, smartphones becomes the digital device with the highest use every day. Because of its portability, it continually threatens to replace traditional devices people used to carry. One of those devices is the DSLR camera. Even though nowadays people can put better lenses and larger sensors into a smartphone, there is still a huge gap in terms of image quality between the images produced by the DSLR cameras and those by a smartphone, especially in a low light environment. The most important reason to account for the difference is that the small size of the lenses equipped in a smartphone limits the amount of light captured by the sensors. In light of this issue, we can make use of deep learning technology to help smartphones produce brighter and cleaner photos, even under physical constraints. This paper, therefore, explores several different deep learning methods, as well as the convolutional neural network, in order to help us to find a potential way of improvement of the brightness of image taken by the smartphone. In this paper, we will focus on the three parts: the convolutional neural network and the generative adversarial network that we have used, and of course, a good database, which is also a crucial part for develop a great network. So, here is the convolutional neural network and the generative adversary network that we have used for this project. So, from the picture, we can see the overall network structure. It on the top one, which is the CNN, it is a fully convolutional neural network that starts with a 9 times 9 layer, followed by 4 residual blocks. In each block, there is two 3 times 3 layers, and each one of them is followed by a batch normalization layer. After the 4 blocks, there are 2 additional layers with kernels of size 3 times 3, and another one with 9 times 9 kernels after the residual blocks. All layers in this network have 64 channels and are followed by a ReLU activation function, except for the last one, which uses 10 for the output. The GAN consists of 5 convolutional layers, each followed by a leaky ReLU nonlinearity and the batch normalization. The first, second, and fifth convolutional layers are threaded with a step size of 4, 2, and 2, respectively. A sigmoid activation function is applied to the output of the last fully connected layer, containing 1024 neurons, and produces a probability that the input image was taken by the target DSLR camera. Then we're going to consider the total loss function that we used for this network. We can see there are 4 different losses that we have applied, which are color loss, texture loss, content loss, and total variation loss. Total variation loss is used to enforce spatial smoothness of the produced images. Then we give each of those loss a corresponding weight, and then we add them up together in order to get the total loss function. Then what next? Because we're talking about the low light image enhancement, then in order to fit the purpose of this topic, we need to find a dataset which consists of enough amounts images with different scenes. I choose the MIT Adobe 5K dataset. Each image on this dataset was taken by the DSLR camera and adjusted by five professional photographers. We first need to modify the original databases so that they can better fit our needs. The brightness of the image depends on gamma value, which is a nonlinear operation. The higher the gamma value is, the darker the image will be. Therefore, if we can adjust the gamma value of each image in the database and make them greater than 1, then we will be able to use the original dataset for project purpose. Based on this conclusion, I write a Python program to automatically adjust the gamma values for each image in database. To simulate real-world scenario, a random gamma value is applied to each image. After evaluating the image, which now has a gamma value ranging between 0.1 to 0.9. Of course, I use the random gamma value in between 0.4 to 0.65. After that, we need to rename those images in numerical order because for the supervised learning, we need to clearly match the input and output image. So for the MIT Adobe dataset, that will be the ground truth. And then for the image with the low light, which we have after we apply the gamma adjustment, that will be the input. Then after that, I write another Python file to cut the original image into smaller patches. Each of them is 100 pixel times 100 pixel, which will be easier to be trained by our GPU. So here is the overall of the result that we get. On the left side, we can see the accuracy in every 1,000 steps. On the right hand side, we could see that we have achieved pretty high accuracy on our training. And here is some examples of the result after enhanced by our network. On the leftmost one is the low light image, and the middle one is the ground truth. On the right hand side, that will be the image after the enhancement. Here is another example. We can see after enhanced by our network, more details used to be hidden in the dark side has been showed after applied on our network. So it seems like we have achieved a decent result. Then what's next? Now we have to consider about improving the network. And for that one, we're going to consider about using the UNet. Here is the overall structure of the UNet. We can see on the left side that is a downsampling process. On the right hand side, which is upsampling process. And the most important step in this UNet is on the upsampling process, there is a concatenating steps on it. It preserves the information from the same level of downsampling process by applying overlap tail strategy. This strategy eliminates the large amount of redundant data produced by traditional sliding window method. Now, in order to predict the pixel of a broader region, the network can learn and predict the pixels by mirroring the input image. This assembled information make the network able to learn more precise details of image and propagate context information to higher resolution layer. Regarding to our project, UNet has the ability to adjust on the shadow part of the image, but also keep the normal part from overexposure. Of course, we should have a better data set. This a more robust data set captured by professional photographer with more scenes will be much better because the MIT Adobe dataset, which is not targeting on the low light environment project, instead of just using the gamma to change the brightness of the image, it's better to capture in a real dark environment. And thanks for watching. That's it.